All right, good morning, everyone. Hope y'all are doing well. I got the test graded last night, somewhere around 9:30. I think I posted grades. The class did very well. The class average on the test was a 90, almost a 92. Compared to the first exam, the average was an 88, so it was very good. This shows the grades from the orange is exam 2, the blue is exam 1. So you can see we had a lot of perfect scores. We had lots of A's, and then we had some drop off here. But for the most part, everyone did well. So I don't think there's really anything to discuss on that. I still have a few students that had some issues that couldn't take the test. So I'm not going to talk about the test at all. I just want to share with you the results for the class. So, you know, everything looked good. And then most of you submitted your work properly. So I had no issues grading things. So everything went good. So any questions before I begin today's material? You all ready to go? I don't have many people on video today. That's okay. Just Taylor. It'll be just Taylor and I today, I guess. All right, we are talking about, we're gonna be moving into a new topic now. But before I get into it, thank you, Kiara. Before I get into it, I want us to just review something that might help us at least get an idea of why we're about to study what we're going to study. We have been talking about lines, and we know that all lines can be written as y equals mx plus b. And we also changed that notation over. We got rid of the y and we replaced it with f of x, just to stress that we could look at it as a function. And so when we have a line, we know that the m in front tells us all about the pitch of the line, and the b tells us where we hit the y-axis, right? So that's our y-intercept. And other than that, other than the slope and the y-intercept, we know that lines are pretty boring. I mean, they keep growing at the same rate. They don't change, it's just straight, right? So let me show you something. I've got something prepared here. Let me take a bunch of stuff off of here first. I know you can't see this yet, but just hang tight. All right, so we know that with a line, right, with a line, I've got a few more things to take off here. Okay, so here's our boring line. And we know that if we change the slope of that line, right, it's going to change the pitch of the line. And if we change, so that's if we change that number in front, right, that'll change the pitch. And if we change the number on the outside, that'll just move the line up and down, and that'll change where it hits the y-axis. So pretty much for every single line that we ever draw, we're always going to have, we're always going to have an x-intercept, and we're always going to have a y-intercept. Would you all agree? For a line, we should have an x-intercept and a y-intercept. There are some special cases where that wouldn't happen. For example, if the slope was 0, let me see if I can get that. There we go. If the slope is 0, then we don't have a y-intercept. An x-intercept. We still have a y-intercept, but we don't have an x-intercept. So there's one special case where we would not have an x-intercept, but every other line has an x-intercept. You could also make the line vertical. Now I'm not gonna be able to make it vertical on here, but imagine that we had a line that was just straight up and down. Then we would have an x-intercept, but we wouldn't have a y-intercept, okay? But other than that, like I said, lines are pretty boring. They just do, you know, flat lines. Now, that is useful in the real world because there are some things that continue to grow at a constant rate. You know, we talk about how much money you make. If you work hourly, then you get paid the same amount every hour. That's going to be a linear function. But the real world is not always lines. The real world can be other things too, things that don't grow or decline at the same rate. And a perfect example of this is, and I'm not sure how this is going to come out on video here, but a perfect example of this is if I were just to take some object and throw it through the air. Now, usually if we're in a classroom, what I would do is I would get a volunteer to go up to the front of the classroom, and I would stand on one end and the student would stand on the other end of the room, and we would throw like a marker back and forth to one another. So when we throw something through the air, right? Just imagine throwing a baseball or anything, throw it through the air. It's going to go up and then it's going to come back down, right? So it's going to look something like, you know, you start with the ball, you throw it, it's going to go up and it's going to come back down. Now that shape that it makes is not a line, right? Obviously it's not a line. So the question is, what is it, right? What is that shape? Well, it turns out that there is an equation or a function that would draw that shape. And it is called a quadratic function or a parabola. And that's what we're going to study today. And parabolas show up all over the place. Okay, so before I actually start getting into what they are, like, you know, what's the equation of a parabola, I want to talk about a few places in the real world where parabolas occur. And you may or may not know this already, but the first example I've given you is a ball, right? We throw any object through the air. The shape is a parabola. Okay, so we call this thing a parabola. Parabola, all right. Now, there's some other places that you might see this. So I don't have a flashlight near me, but if you have ever used a flashlight that has, you know, like the handle, and then it has that thing on the end where the bulb is, and the front of this, you can turn that. Have you all ever seen that on a flashlight? You can turn that thing on the end, and what does that do? Can someone tell me what that does with the light when you turn the end of it? Do y'all know what I'm talking about?
Yeah, it turns the flashlight on.
Okay, so it might turn it on, but what does it do to the actual light? Have you ever noticed when you turn the end of a flashlight? Okay, I see Kiara doing it. It like takes your light and either like spreads it out real wide, or it makes it like a narrow beam, okay? So what's actually happening in there, and I'm gonna have to kind of like give you a visual, so forget this for now. Inside you have a little light bulb. Okay, so the light is coming out in every direction. Okay, so light's coming out, but within the front of the light, there's this big mirror. Okay, there's a mirror. And what that mirror does is the light that hits it, okay, so these little light rays hit the mirror, and when they hit the mirror, they bounce off, and they come straight out like this. They bounce, and they come straight out. So all these little beams of light are bouncing, coming straight out, and that happens all the way around the lens. And all these little rays of light come out, and that's what gives you the shape of the light as being a beam. Okay, that mirror in the back, that mirror that they use, that mirror in blue here, is not just some arbitrary curved piece of mirror. It has to have a very special shape. It's not a circle, it is a parabola. And so if you use a parabola and put a light source in front of it, a parabolic mirror, and put a light source in front of it, then all the beams of light will come out. Well, if you get it positioned properly, the beams will come out straight, and you get this nice focused beam of light. Now, when you turn that handle, what that does is it moves this mirror either forward or backwards. So it might move the mirror backwards. If it moves it backwards, what happens is those beams of light, I'll do it in a different color, they come out, but instead of coming straight out, they come out at slight angles like this. And so what you wind up doing, oh, I kind of overdid it there. What you do by turning that thing is you move that mirror, and so it spreads the beams out. Does that make sense to you? but that's all based on a parabola. Okay, that shape has to be a parabola. So it's the same shape that a ball travels, you know, that same shape that a ball makes through the air. Just turn it sideways and put a light there, and you've got a flashlight with a beam. Your car headlights work the same way. If you've ever looked at your headlights on your car, you'll notice that in there it's like silverish behind the light bulb. Well, that's your parabolic reflector behind the bulb. And so when you turn on, you know, your low beams, high beams, when you turn your high beams on when you're driving, it's really bright and it's like a straight beam of light. That's using this property. Now there's something else that we have in the real world that you probably are completely unaware of. Maybe you know. Everybody uses a cell phone, right? We all have phones, right? So what happens? We're sitting here right now. Let's say I make a phone call, right? So I sit here and I call somebody, or I text someone, or I, you know, do something on Twitter or whatever it is, right? What's happening? Well, this phone is sending out an electronic wave. Okay, it's electromagnetic radiation. It's stuff you can't see with your eye, but it's there, right? It's physically, this electromagnetic wave is traveling out from this phone in every direction, through your walls, through your body. It's going everywhere, right? If we could see it, okay? If you could see the stuff coming out of your phone, like if we could see it, we'd be blind. It would be like someone turned on this huge light that just blinds us because it's everywhere. So that comes out. So here's your phone. Here's you. Okay. Yes, I know, it's a really good picture. Here's your cell phone. You got the biggest cell phone they offer, okay? And you're gonna call your friend who's over here on the other side of the city, right? And so what happens? Well, your phone is sending out the signals everywhere, right? It's going in every direction. And somewhere near you, within a few miles, is a cell phone tower. And that cell phone tower is really tall. And what it has on it, if you ever see these, they have these things that look like little boxes on them. What those actually are parabolas. They're little parabolic, they're parabolic collectors. And what they do is they take, and I'll show you a zoomed in picture of what this box looks like. It's a box, but behind it is like a parabola. So your electromagnetic waves go into this, and they do the opposite of what the light beam did. It's going to bounce off this, and there's this thing in the middle of the thing, you can't see it, and your beam comes in, hits here, and that little black thing is the receiver. It gathers that signal, okay? So it's sitting there, the tower is like listening, okay? But it's listening with these parabolas, and it gathers that signal, okay? So it takes your signal in, and then what it does is it amplifies that signal and sends it out everywhere, okay? And then there's another tower that's going to pick up that amplified signal and send it to the next tower, to the next tower, to the next tower, until it gets to the tower near your friend, and your friend's phone is always listening too. And so it's going to receive that call that you made. And that all happens at the speed of light. So, you know, we don't even notice it, right? We call, the phone rings over there, but all of that's happening all in an instant, which is amazing, isn't it? I mean, I think that's amazing that that happens. But it's all dependent upon this parabolic shape, this parabola, that gives you the ability to listen and gather the information, gather all those electromagnetic signals and process them, right? And send them to the right person, which is crazy that everything gets sorted properly and goes to the right place, but that's the way it works. And one other illustration of this is kind of the same concept is, you know, if you want to talk to somebody, let's say you're here on this side of the earth and your friend is on the other side of the planet. Well, we don't have towers going all the way around the planet because there's oceans between us, right? So what we do is, if you want to make a call, we have satellites sitting up here in space. This is my satellite, thank you very much. And we might have multiple satellites sitting in space. And so same thing happens. You make your call, the tower catches your call, the tower sends that signal up to a satellite. The satellite has a parabola that's listening, right? That satellite sends it to the other satellite that has a parabola that's listening. And then that sends that down back to a tower over here, and then that goes to that person. So instead of going across the ground through towers, we go up through space and then come back down to the ground. All at the speed of light. It's crazy. It's crazy when you think about it. So, like I said, if we could see all the stuff that's in the air, think about all the things that are in the air right now. Everyone here probably has Wi-Fi at home, right? You have a Wi-Fi connection, right? If you could see those beams, you would literally be blind. You would not be able to walk in your house because it would just be everywhere. You've got your Wi-Fi, you've got your cell phone, you've got your cellular network is, you know, out here, right? You can connect to cellular. It's all around us, everywhere. So anyway, okay, so have I kind of convinced you that parabolas are useful and important in the real world? I mean, they have a purpose. That's really what I want to do, just kind of lead into this saying, you know, like, why would we ever study parabolas? Because the engineers need to know exactly how they work and how to replicate them, how to produce a mirror that has that shape, how to produce these towers to have that shape. If you don't have that shape, you can't listen. All right, so we know what lines are. They're kind of boring. Parabolas seem to be a little more interesting. So what we'll start with here is, I'm going to call it a parabola, but we're going to be talking about what are called quadratic functions. Okay, this is what we call parabolas. Okay, so all quadratic functions, all parabolas can be written this way. Y equals ax squared plus b times x plus c. So I want to put the line back up here. Just next to this, I want us to be looking at the line. I hope that you agree that when we were looking at the line, the m was just a number, wasn't it? It gives us the slope. And the b was just a number. So a specific example of a line would have been y equals 2x plus 1. That's a specific example of a line. For a parabola, what we have is, yeah, we have a number in front of x, don't we? See that number? It's a b. That's a number in front of x. We have a number by itself, which is kind of like the m was here and the b was here. So a number in front of x and a number by itself, just like the line, but we've added something new. What we've added is this entire piece here, which is a number in front of x squared. So we've added an x squared to the whole thing. And when you do that, you no longer have a line, you have a parabola. So a specific example, let me just give you a specific example of a quadratic function. It would be something like, I don't know, I'll just make it up, 2x squared minus 5x plus 2, okay? I'm just making that up. That is a specific example of a quadratic function or a parabola. So we need to know when we see them, you know, what we're looking at, make sure we know it's not a line. So the biggest thing for you to be looking for is, do you have an x squared? If you have an x squared in there, it's a parabola, it's a quadratic. All right, now we just talked about what happens with a line. If you change the m, what happens? The pitch of the line changes. If we change the b, the line moves kind of up and down. So over here with the parabola, we kind of want to know the same thing. What happens when you change the a? What happens when you change the b? What happens when you change the c? So I put together a little animation thing here to kind of help us with this. Just give me a second to get it all back in order here. Okay, so there's an example of a parabola, all right? Now, I don't know if you can see this. Yeah, you can see that all right. This says that it's y equals 1x. You know what? I put the wrong thing there. Sorry. Okay, this is y equals 1x squared plus 0x plus 0. So this right here, what we're looking at is the parabola y equals x squared. That's the most basic parabola you could ever have. It's just a 1 sitting in front of x squared. Notice that we don't have any x here and we don't have a number by itself. It's just y equals x squared. And that gives us our basic parabola shape. Okay, so parabolas look like U's, okay, like a U. It's not a sharp corner, right? It's not a V, it's a U. Now, let me change the value of A. Okay, so I'm gonna change the value of the number in front of x squared. So let's see what happens if I let A get bigger. I want you to just watch what happens to the graph. If I let A get bigger, the parabola starts to, I don't know, how would you describe what it's doing? What is that doing?
Narrowing?
It's narrowing, isn't it? So the bigger that A is, the more narrow it gets. Now let me let A get smaller again. It's gonna flatten back out. What do you think is gonna happen? I don't know if you can see this very well, but this right here is telling you what the value of A is. Right now I'm at 1.6. Let's see what happens. If I go to 1, I'm back here, 0.8, 0.7, 0.6, 0.5. What's happening now? So when the A was getting bigger, it was getting narrow. Now I'm letting A get small. What's happening?
It's beginning to line.
Flattening out, isn't it? It's wanting to flatten out. What do you think is going to happen if A becomes negative?
It's gonna flip.
It's going to flip over. Yeah, good. See, so look, by A being negative, what happened was the parabola flipped over and now is kind of down instead of up, right? So A, the number in front of the x squared, has complete control over whether or not this thing opens up or down. Okay, so I'm going to go back to my notes real quick and I'm going to say this. I'm going to say A controls if parabola opens up or down. If A is a positive number, so greater than 0 means positive. If A is positive number, then the parabola is going to go like this. It's going to open up, right? If A is negative, then the parabola is going to open down. I always remember it, you know, positive people like to smile, so positive, smile, right? Negative people are always grumpy, they like to frown, so it looks like a frown. Okay, so that's what A does. All right, let me put A back to a positive number. All right, there we go. Now, let's see what C does. I'm going to skip B for now. Let's see what the C, changing C does. What does that do?
It changes the Y-intercept.
Yeah, it's just changing the Y-intercept. Isn't that just moving our parabola up and down? Right, that's all it's doing. We're just changing C, it's just moving it up and down, right? Wasn't that exactly what that number did with our line, that B? B for the line moved it up and down. So that's what's happening here for us with the parabolas. The C moves the parabola up or down. Oops. It changes the Y-intercept. Right? So the C has control of the shifting of this thing up and down. So what do you think the B is going to do?
Determine whether
I'm sorry, determine whether what?
whether it moves left or right on the line.
Yeah, so maybe it has, the B has some control of our left and right. Let's see. Let me take C back up here. I'll just put it here. And now let me try and control the B. Ooh, wait a minute, look. B is doing some weird stuff, isn't it? It's not just moving it left and right, not just left and right, right? There seems to be more involved there. Do y'all agree with that? It's not only moving left and right, it's actually moving kind of up and down too. Yes? So B, I'm gonna say this about B. B just moves it, okay? But we just kind of, it's not clear to us how it moves it. It does some stuff, but it does move it around. Agree? Left, right, up, down, but we just can't, it's not obvious. And that's okay, we don't need to know, all right? We don't need to know. We just need to know that all of these things do something to the shape. I should also point out here that the parabolas that we're gonna study here in this class, we will only study parabolas that open up or down. You can have a parabola open left and right, but it's a different equation and we're not gonna study it here, all right? We're just gonna focus on parabolas that open up and down. Okay, now, let's go back to the picture. Let's talk about intercepts, all right? Yeah. So take a look at this parabola here. Do I have X-intercepts? Does my graph hit the X-axis? Yes.
Yes.
How many X-intercepts?
Yes, in 2 spots.
Yeah, it hits in 2 spots. With a line, remember with a line, we had one X-intercept, right? Just one, and sometimes we didn't have any. But with the parabola, it looks like we hit the X-axis twice, right? How about the Y-intercept? So we had 2 X-intercepts. How about the Y-intercept? Do we have a Y-intercept?
Yes.
Yeah, we have 1, right? So there's 2 X-intercepts, and there seems to be 1 Y-intercept. And then we have a very important point that we did not have when we were talking about lines, right? With lines, they're boring, just straight. With the parabola, we have a very, very special point. And that point is this one, and it has a name. It's called the vertex. Every parabola has a vertex, every one of them. And how would you describe to me, if you were just trying to explain to somebody who's not real into math, what the vertex of a parabola would be? Just in just common words, how would you describe that point to me?
The lowest or the
lowest point.
Yeah, it's just the lowest point on the graph, right? That vertex appears to be the lowest point on the graph. Now, I'm gonna mess you up now. Oops. What if our parabola went that way? So look at this. Do we still have 2 X-intercepts?
Yes.
Yes. Do we still have a Y-intercept? Yes. We have a vertex. Is the vertex the lowest point on the graph?
No.
No, now it's the
Highest point.
highest point, right? So, but that's it. That's all a vertex can ever be. It can only be the lowest point on the graph or the highest point on the graph. If your parabola opens up, okay, if your parabola opens up, the vertex is the lowest point. If your parabola opens down, your vertex is your highest point. Understand? Now let me ask you a question. I just said that every parabola has to have a vertex. Okay? I hope that you agree with that. If I ask you to draw a U that opens up or down, that you're going to have a lowest point or a highest point, depending on how you draw it. Does anyone have any reservations about every parabola having to have a vertex? Okay. Does every parabola have a Y-intercept?
No.
It doesn't have to.
So how could I draw a parabola that did not have a Y-intercept?
It would just be either like on the right or left side.
Okay, good. I'm glad we're talking about this. Okay, so you're saying that maybe if I draw my parabola over here like this, that.
Oh wait, no, because it keeps going out, right? So it'll eventually touch.
Yeah, exactly. So we have to be careful with this because what would happen here is, I can't zoom out on this, but let me do it this way. Let me clear everything out of here, go back to, let me move this parabola over. Maybe I can get, not maybe. Let's do this. I'm gonna take this back, to 0. It'll be much easier if I do it this way. There we go. Okay, here we go. I think this is a good illustration. Right now, it looks like this parabola does not hit the y-axis. But the problem is, if you zoom out, eventually it's going to. Even if I make this very narrow, I have to make it really narrow and try and move it over. Having trouble, oh, I'm moving the wrong thing. Try and move this over. So even if we make the parabola really narrow, eventually it has to hit the y-axis, no matter what. So these parabolas, they look like U's, but they keep spreading out. Eventually, you're going to go in both directions forever. Does that make sense? So if it has to spread out in both directions, doesn't matter where you put it on the graph, you have to have a y-intercept. So I'm going to write this down because we need to know this. All parabolas have one vertex and one y-intercept. Okay, all parabolas have one vertex and one y-intercept, guaranteed every time. Now, let's talk about X-intercepts. So in terms of X-intercepts, how many X-intercepts do I have there? Oh, sorry, I moved it. How many X-intercepts do I have?
2.
2, okay. Is it possible to have 3? Can I draw a U that would have 3 where it hits this x-axis like more than twice?
No.
No, it'd be impossible. So it looks like 2. Now, is there a way to have 1? How about if I do this? What if I place the vertex? Come on. I can't do it. Let me do this. I have to move this back. Sorry, give me a moment. Having trouble. Okay, what if I place the vertex right on the x-axis? There we go. Yeah, what if I put the vertex right on the x-axis? Then isn't the vertex the x-intercept? And that would be the only point that hits. Does that make sense? Are there any questions on that? Let me change that to 1, change that to a 0. And change, oh wait, change B to 0. There we go, that's what I'm saying. So if I move the parabola where the vertex is on the x-axis, then I only have one x-intercept. Is it possible to have no x-intercepts? How about if I do this? Just move it up like that. Do you all agree that that parabola is never going to hit the x-axis? Okay, so when it comes to parabolas, this is kind of what we're going to take from this. In terms of x-intercepts, you either have 0, 1, or 2. And all of that is going to depend on the parabola that you're given. All right, so in summary again, just if we were to wrap all this up, go back to the notes, and I'll kind of jot this down again. We know that A controls the up and down. If A is positive, it moves up. If A is negative, it goes down. C moves the whole parabola, shifts it up and down. Okay, changes the y-intercept. B moves it, but we're not quite sure how. we always have one vertex. We always have one y-intercept. And we either have 0, 1, or 2 x-intercepts. Okay, every parabola has these properties. So our goal now is to go and see if I were to give you a parabola, could you graph it? Could you sketch it? Just like we did with the lines. I gave you an equation of a line, asked you to sketch it, right? That's what we want to be able to do here. I give you the equation of a parabola, you draw me the picture of it. All right, so in order to draw it, you're going to have to determine all of this information. So let's start with an example, all right? So your first example is we want to sketch the parabola f of x. I'm going to use f of x instead of y. F of x equals, let's start really basic here. Y equals 4x. Y equals x squared minus 4x minus 5. All right, so we want to sketch this. All right, first things first, let's identify a, b, and c. So a is the number in front of x squared, b is the number in front of x, and c is the number by itself. So who wants to tell me what a, b, and c are?
A is x squared.
Okay, close. Remember, a is the number in front of x squared.
1.
1. Okay, so this a, b, and c, these are always going to be numbers. So we're going to have 1 here. Okay, how about the b? What is the number in front of x?
4.
4. Okay, what about the negative there? Should we keep
The negative 4.
Yeah, so we'll keep the negative. We'll make sure we account for that, minus 4. And then what would c be? The number by itself.
Negative 5.
Negative 5. Okay, are there any questions on how we identified a, b, and c? Okay, well, that's the first thing you always want to do when you have parabola. Just figure out what a, b, and c are. Now we need a process. Okay, we need a set of steps to follow in order to get this sketch going. All right. So here are the steps. I'm going to write the steps on the side, and then we are going to use those steps to do this problem. So steps to sketch quadratics, or if you'd like, you can call them parabolas. All right, first step is to determine if it opens up or down. So that's a question you have to answer. So let's go ahead and answer that question for this problem. Does this open up or down?
Up.
Up. This opens up. Why? Because a is 1, and 1 is a positive number. It's greater than 0. If you have a positive number in front of x squared, then you know that the parabola opens up. Okay, that's the first step. The second step is to find the vertex. So that means we want to find the either highest or lowest point on the parabola. In this particular problem, would this be the highest point or the lowest point? So think about what this parabola does. Opens up or down?
The lowest point.
It'd be the lowest point because we know this parabola opens up, right? We know that this parabola looks like this already. Okay, we know that, right? So now we need to find, we're going to try and find that vertex. We're going to try and find that lowest point. Now, to find it requires a formula that you have not been given. So I have to give you this formula right now. All right, so to find the vertex, we first have to understand that whenever we're talking about the vertex, this vertex here, well, I'm going to draw it over here. When you talk about the vertex, I'll do it here. This vertex, do you all agree that that's just a point? Right? The vertex is just a point. It has an x coordinate and a y coordinate, right? Now, when we talk about vertexes with parabolas, we don't use x and y. We actually call the x coordinate h and the y coordinate k. Now, that's just to let you know, look, this is a very special point. It's not just any XY on the graph, it's the vertex. And so we give it a special label. But it's still at the end of the day just a point. You're just going to plot it. So here's the formula. H, if you want to know what H is, all you have to do is calculate this, negative B divided by 2 times A. All right, so what we're going to do is we're going to take whatever B is, we're going to change its sign and divide by 2 times A. So when I'm sitting here saying B and A, I'm talking about the B's and A's that we found already. Okay, so all we have to do is plug these numbers into that formula, and that will give us H. Now, you might be wondering, like, where does this formula come from? Like, where is it? Like, how did we get that? And I'll just tell you this. It comes from calculus, which is beyond this class. So if you get to calculus, we actually prove where this formula comes from. And then we use it here, but it's actually proven later on. Okay, so you just have to take that on faith, that that's what it is. So back with us, step 2, we're going to try and find the vertex here, which means we need to find what H and K are. First, I know that H is negative B over 2A. I know that because that formula was given to me. And now I have to find out what negative B is. So this might be a little bit of a tricky part. B is negative 4, right? B is already negative 4. So what would negative 4 be? You see what I'm saying? You have to take the negative of whatever B is. So if B is already negative, you've got to do the negative twice. Carolyn, I think you said that it would be what?
Positive.
Positive, right? And then we have 2 times A. A was 1. So this becomes 4 on top, right? Negative is positive. And then on the bottom 2. So 4 over 2 is 2. So we know what H is. With me? Now we need K. So back over here on the side with the steps, I need to tell you how to get K. And again, it's a formula, but it's kind of a weird formula. What you're going to do is you're going to take your function and you're going to evaluate it at H. Now, we just had a test over this. If somebody gives you a function and asks you to plug a number in, you could do that, right? I mean, that's part of what you're tested on. We have a function here, don't we? Our function is the quadratic. What we need to do, what this is saying here in green, is that we need to take the original function and plug in, replace the x with h. But we just found h, didn't we? We just said h was 2. So for us to figure out what k is, what we're going to do is we're going to take the function and we're going to plug h in, which means we're going to be plugging 2 in. And the 2 is coming exactly from the fact that we had 2 as our answer there. So what happens if you get h wrong? What if you calculate h to be incorrectly on a test? What can you tell me about k? It's going to be wrong, right? If you get h wrong, k is going to be wrong. So you have to be real careful. Make sure you get h correct here. So now we plug 2 into this function. So I'm plugging it into this thing up here. So we have to do 2 squared minus 4 times 2 minus 5. This is 4 minus 8, order of operations minus 5. This should give me negative 9. Any questions there? So remember, this is a point. And the point that we have, the vertex, right, is the point 2, negative 9. 2, negative 9. If I asked everyone to go plot 2, negative 9, you could do that, right? You go to the right 2, down 9, you put a dot. All right, you all ready? Move on to the next step. Okay, the next step, and I should warn you here that if you've done parabolas before, or if you plan on going and getting tutoring on this, I can almost guarantee you that no one that I know does it this way, all right? So if you're with a tutor and you show them this step or something, they're like, what the hell is that? Just just trust me that I think this is the most efficient way to do this. This is my opinion on this. But I think after you see it, hopefully you'll agree. What we're going to do on this is what I call a quick sketch. A quick sketch. Now, I want us to do the quick sketch first, and then let's talk about why you think that I think this is a good step. Okay? So right now, step 3, I'm going to do this quick sketch. Right, what is the only information I know about this parabola right now, though? There's only 2 things we've figured out. What is it?
The vertex.
The vertex and?
It opens up.
It opens up, right? That's all we know. But that's actually a lot of information, okay? Because watch, I'm going to do a quick sketch. And when I say quick, I mean real quick. I'm not even going to label, like, do little dashes or anything like that. I'm going to start by putting my vertex. If I did my vertex, I need to go to the right 2 and down 9, right? To the right 2, down 9. I'm not even going to measure it. I'm just going to go to the right a little bit and down. I'm just going to plop a point there. Everyone see that's my vertex? Okay. And the parabola opens up, right? So this is the lowest point. So I know that my parabola does something like this. Why do you think I did that step? What does that picture tell us right now?
Kind of where the X-intercepts would be.
Almost. It's kind of like, it's not that we know where they are, but we know how many we have, don't we?
Mm-hmm.
We actually have 2 X-intercepts. We have to have 2 X-intercepts. What if this parabola would have opened down? So let's just say in the very first step, we would have had that it opened down. Then what this would have told us is that we have how many X-intercepts? None, right? We have none. Does that make sense? What if our vertex would have been right here on the x-axis and it opened up? How many X-intercepts would we have?
1.
1, but wouldn't it be the vertex? Yes. So this little quick sketch, all it does is helps you determine how many X-intercepts you have. So the quick sketch, right, we do a quick sketch and then we determine how many X-intercepts we have. If we have 2, go to step 4, all right? If we have 2 X-intercepts, we're going to do a step 4. If we have 1, well, what did we say? If we have 1 X-intercept, then it has to be the what?
Vertex.
Vertex. Then it's the vertex. So we have it already. And if we have none, then what can we say? Well, let's not go try and find them, right? Let's not try and find X-intercepts that don't exist. So if we have 0, we're going to go to step 5. If we have 1, it's vertex, and then go to step 5, all right? So what is step 4 then? Step 4 is if we have 2 X-intercepts, right? If we have 2 X-intercepts, how do we find them? So we find the X-intercepts. And to find the X-intercepts for any function, here's what we do. We take the function and we set it equal to 0. Be careful with what I just put down here. I did not say we plug 0 into the function, right? I didn't say take all your x's and replace them with zeros. I said take the function itself and set it equal to 0. Ask yourself when it's 0. So that means we have to solve this equation. We have to solve ax squared plus bx plus c. That's our quadratic. We have to set it equal to 0. Now, when we were dealing with lines, it was much easier to set a line equal to 0 than setting that equal to 0, because that is called a quadratic equation. Now we have a problem. The question becomes, how do we solve quadratic equations, right? Do we have a method for that? And there are basically 3 methods. You can factor, okay? So I think I want to do this kind of as its own little step within this. How to solve ax squared plus bx plus c equals 0. To solve that quadratic, your first option is to factor. Now, if you're not good at factoring or you feel uncomfortable with it, then your second option, okay, so these are options. These aren't like step 1, step 2. The other one is to use the quadratic formula. And I am sure that y'all have seen this at some point in your life, this formula that basically the quadratic formula gives you the answers. You just have to be able to plug in. So here's the formula. Your answers, x, are negative b plus or minus the square root of b squared minus 4 times a times c, all divided by, the whole thing divided by 2a. Y'all seen that formula before? Somewhere in their past, you remember seeing that? I would provide that formula to you on the test. I would also tell you on the test, I would tell you not how to do each of these steps, but I would just remind you, okay, determine if it opens up or down, find the vertex, do a quick sketch, find the X-intercepts. I will give you each of the steps like just very generally. You have to know how to actually execute each step. But I would give you the quadratic formula. All right, so that's how we're going to solve. And so let's do that step over here with our work. I'm gonna go to, so I did the quick sketch. I have 2 X-intercepts. Let me get rid of that one. From the quick sketch, I know I have 2 X-intercepts. So I'm gonna go to step 4. I'm going to find the X-intercepts by taking the original function, which was x squared minus 4x minus 5 equals 0. And now I'd like to solve that equation. I'm going to do it both ways. First way I'm going to do it, I'm going to factor. And again, if you don't recall how to factor, don't worry, because you're going to have the quadratic formula. But I just want to show everyone how fast this is if you're comfortable with factoring. So for those of you who are comfortable with factoring, you should know that that turns out to be, does anyone here know what that turns out to be if you factor it? Can someone tell me? It's x something times x something? No? Minus 5 plus 1. That's what it turns out to be. So if you're uncomfortable on this step, don't worry, because you have the quadratic formula. But if you could do that quickly, then all you'd have to do now is set each of those equal to 0. Set that to 0, set that to 0. Then solve each of these like little linear equations. So add 5 to both sides. So you get x is 5. And then subtract 1 from both sides, and you get x is negative 1. So if you can factor, that's a very quick process. You just get your 2 answers, 5 and negative 1. If you can't, you have to use a quadratic formula. I'm just going to put QF. And that means you need to use this formula here in yellow. And the formula, it's nice to be able to use a formula, but students seem to have trouble with this because they plug things in and they mess up the numbers. So just be very careful with it. We're going to say x equals, okay, now for us, what is negative b? Be really careful. What's negative b? So remember what a, b, and c were? Maybe I should grab this. Let me grab this and bring it
negative
down.
4 plus negative would be positive.
Yeah, so I'm gonna just drop that off over here so we can look at it. So B was -4. So we're gonna do -4, so that's +4. We had that same thing happen when we were doing the vertex. So 4 plus or minus square root. Okay, next thing we have to do is take B and square it. So take B, -4, times itself. -4 times -4 would be? Negative times negative is?
Positive.
Positive, so we should get positive 16. Okay, -4 times A, what's A?
1.
1, okay, times what's C?
-5.
-5. Okay, I'll figure that out in a minute. All divided by, the whole thing divided by 2 times A, but A for us was 1. All right, let me continue. 4 plus or minus square root. Okay, this is where most students mess up, this part right here. So my advice to you is this. That number, just always bring that number down, 16. Let's just drop that in right there. This is the part that students have trouble with. So here's what I would recommend you do. Look at these things right here. How many negative signs do you see?
2.
2, right? If you have 2 negative signs, your answer will be positive. All right, 2 negative signs, your answer is positive. If you have 3 negative signs, your answer is negative. If you have 1 negative sign, your answer is negative. So in other words, if you have an odd number of negatives, your answer will be negative. If you have an even number of negative signs there, your answer will be positive. Does that make sense? I have 2 negative signs, so my answer will be a plus. So I'm going to put a plus here. And then all I want you to do is just take the numbers and multiply them together. Don't just ignore the signs completely. What's 4 times 1 times 5? So 4 times 1 is 4, times 5. That should give you 20, right? Okay, so we have plus 20. All of that divided by what?
2.
2. Okay, still taking my time. 4 plus or minus square root. All right, square root of, we need to add those numbers together, don't we? What is that? 16 and 20, that's 36 all over 2. Now, another common mistake I see right now is that students will try to like do 36 divided by 2, or they'll try and do the 4 divided by 2 or something like that. You cannot do that, all right? You have to remember that this division bar is almost like a parenthesis. You have to do everything on top first, then divide by 2, all right? So how about the square root of 36? What does that mean? We're saying square root of 36, that means what number times itself is 36?
6.
What is it?
6.
It's 6. So that just becomes 4 plus or minus 6 all over 2, right? So on this step, the square root of 36, that whole thing just becomes the number 6. That's what the square root means, right? Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. Square root of 25 is 5. So you have to know some of the perfect squares if you're going to be able to do that. And now this part right here, this is what I like to do here. That plus or minus right there means we have 2 different scenarios that we have to look at. So I like to draw little arrows. I like to do like my 2 different cases here. I do the plus case here and the minus case here. So if I use the plus, it's 4 plus 6, and then divide by 2. 4 plus 6 is 10, and if I divide 10 by 2, we get 5. Now, if I do the minus right there, then it's 4 minus 6 over 2. 4 minus 6 is negative 2 divided by 2. Negative 2 divided by negative 2 is negative 1. Is everyone clear on what I did on these two cases? Look at our answers. 5 and negative 1. That's the same thing I had here. 5 and negative 1. Much longer process. Lots of places you can make mistakes, but you get the same answers. All right. How are we doing on time? Okay. So now we've done step 4, right? We've found the x-intercepts. We have them. We have both of them. They're 5 and negative 1. So what's the 5th step? And unfortunately, I don't have any more room here. Maybe there's a way I can squeeze this in. I don't think I can. Here's what I'll do. I'm just going to take all of this and move it right there. I'll put it right there. Yeah. Get rid of that. Okay. Because I want to continue my steps over here. Okay, the 5th step. We've done so much, let's try and remember what we've done. We determined it opened up, right, up or down. We found the vertex. We did a quick sketch which told us how many x-intercepts we had. We went and found the x-intercepts using this. What do we still need to find on the graph? What have we not gotten yet? The x-intercept, the vertex. What does every parabola have?
The Y-intercept.
The y-intercept. Good. So we want to find the y-intercept. I have good news about the y-intercept. I have really good news. All you have to do is this. Plug 0 into the function. So now, instead of setting the function equal to 0, you get to plug 0 in. And that's a good thing. So I'm going to do that step 5 here. The y-intercept, what I do is I take the original function and I plug in 0. So that means I'm going to do 0 squared minus 4 times 0 minus 5. So I'm taking that original function here and just replacing x's with zeros. And what comes out? Negative 5, right? That's all that happens. These go away. You just get minus 5. The last step is a sketch, is your final sketch, your final picture. So I'm going to do that on a new page. And I'm going to give myself some graph paper. I'm going to do a nice XY axis like this. All right, so we start putting all the information down here. I'm going to start with the vertex. All right, so remember the vertex was 2, 9. Right 2, down 9. 1, 2, 4, 5, 6, 7, 8, 9. There's negative 9. There's positive 2 there. I'm going to put a vertex here. I'm actually going to label it 2, negative 9. I'm going to do that so that everyone knows what that point is. Okay, that's my vertex. Now, the next thing we found is that we had 2 x-intercepts. Where were they?
Five and negative 1.
5
5
and
and
negative 1.
Good. So let me go to 5 first on the x-axis. 1, 2, 3, 4. Here's 5. I'm going to put a dot here. And then I have to go negative 1, which is right there, and I'm going to put a dot there. Okay, I've got my vertex. I've got my 2 x-intercepts. One more thing we found was the y-intercept, and the y-intercept was negative 5. So I just go down 1, 2, 3, 4, 5. Here's negative 5, and I put a dot here. And now I have all the information I found, right? Everything is here. Now, something I did not talk about that I wanted to wait till right now to talk about is this final step of drawing the U. Okay, we don't want to be here like this and just be like real sloppy, like, like that, okay? We want to be a little bit better. We want it to look like a nice parabola. So one thing to keep in mind is that if you could imagine having this imaginary line, okay, this is not part of the parabola, this imaginary line right down the middle, your parabola has to be symmetric to that line, meaning that it has to be a perfect reflection of itself over that line. So what I like to do is this. I like to start at the vertex and just draw myself a little U here. Okay, I make it a U shape because I want to make sure it doesn't look like a point. It's not a point. And that kind of sucked. I think I'm going to start. I'm going to draw a little U. And then what I'm going to do is I'm just going to very carefully connect the dots on the left side together like this. Draw an arrow. And then I'm going to try my best to mirror that on the other side. This does not have to be perfect, but when you step back and take a look at it, it should look decent. What I'm saying is I don't want it to look like, you know, the left side look like that and then the right side look like this. Right? Everything should be a nice U shape. There it is. Okay. Any questions? This is obviously just the first example. So for tonight, for homework, I'm going to give you 3 problems to work on your own, all right? And just try and follow the steps that we followed here. All right, so I'm going to put these on the side. Don't worry about any homework out of the packet. Just do these 3 problems. So this is your homework. First problem. Once you, all of these, you just follow those same steps that we just did. First one is x squared plus 6x. Trying to think if I want minus, hold on. 16. Next one, f of x equals x squared minus 10x minus 3. And the third one, this one will be, this one I won't be so nice. Things are going to get a little weird here. I'll make that at least, let's make that 10x. Okay, do your best on that third one. I will already warn you on the third one that you're going to get decimals. So you're going to need your calculator for that, okay? Also, on the second one, you're going to need your calculator. At some point, you're going to need your calculator for the square root. Remember on the problem we just did, we had square root of 36, and we just said that was 6. You're probably going to have something like square root of like 10 where you don't know what it is. You're going to have to use your calculator to do that. So if you get hung up on any part of it, just see how many steps you can get out of the 6 total steps. And we can come back and talk about that next class. Are there any questions on this?
Could you go back to the notes? Like
yeah, let me grab this. And you want me to go back to where I had the steps? Is that what you're saying?
Yeah, if you could just scroll down. Sorry, I need to take a picture of it, that's why.
Okay, I can zoom this out a little bit. So, you know, we're going to end class here. Do you have the picture yet?
Yes, thank you.
Okay, anyone else? Want to picture that? Say again?
Could you go back to the sketch?
Here, I'll do y'all one. Oh, I'll do y'all one even better. I'm just going to export this to a PDF. And I'm just going to put, I'm just going to email, well, here, hold on. 13, 14. Let me do this. Notes. Okay, I'm just going to send it in the chat. Okay, so in the chat, I just put all the notes from today. All right. Is that fair? Okay, if for some reason you can't get it through the chat, I can send it email. So I just want to say one more thing about parabolas. I was talking about where you see them in the real world. You know, there's something, if you look back over history, the history of humans, a lot of advances in math and technology has been because of our unique desire to want to kill one another, right? We all, I mean, human beings have this, seems to have that we have this inherent thing where we just can't get along, right? We're always fighting wars and doing other things, right? We want to go conquer each other. Well, historically. So if you think back to like the medieval days, I guess, where you had these castles, right? You had these towers and you had this castle. I know this is a wonderful castle. You know what, I'll make it a little bit three-dimensional. So you have this castle, and you know, the whole idea was this army would show up and all these soldiers would want to try and storm the castle, steal the food and gold and everything else, right? But they had to get past the castle wall. Well, they started to kind of like use catapults, right, to launch things to try and, you know, take out things on the tower or within the castle. Well, everything they threw through the air, right, traveled in a parabolic path. And at some point, humans started to understand the mathematics behind the parabola. So instead of just like arbitrarily lobbing and just hoping that you were going to hit where you wanted to hit, once we understood the math behind it, we were actually able to say, okay, we want to hit here, right? We want to hit that red dot. Well, guess what? That red dot is an X-intercept of a parabola. That's all it is, right? It's where the parabola hits the x-axis. So maybe we can come up and figure out what function would draw that parabola. In other words, we could put the settings on our catapult to fit the model for the quadratic that would make sure that that's going to hit there, right? I know that sounds like ridiculous, but that's these types of things are what pushed that pushed our math, pushed our technology. Now we can drop a bomb on pretty much anywhere on the planet within a few feet from outer space, pretty much. You know, so you know, this evolution required an advance in mathematics and an understanding of certain functions, including the parabola. So I've always just kind of been amazed at how much warfare has pushed technology. Same with like the atomic bomb, right? The atomic bomb, our understanding of the atom was because we were in a race with Germany to see who was going to come up with that bomb first, you know, and whoever got it first would have a major upper hand. So yeah, anyway, all right, I'm just blabbing. Y'all have a good day, y'all have a good weekend, and I will see you on what, Tuesday? And we can talk more about parabolas.
All right, thank you, sir.
All right, have a good one. Good job on the test.
sir.
Thank you.